Dominika, if I pronounce it correctly, who will talk about JSON Web Tokens.
Hello everyone, my name is Dominika, and today I'd like to talk to you about JWTs, or JSON Web Tokens. JSON Web Token is an open standard that defines a secure way of exchanging information between the two parties. It was first introduced in 2010 and then formally accepted in 2015. Ever since, it has greatly evolved in response to its growing popularity. So JWT is a base 64 encoded JSON message. It has been created for a scenario where there is a need for a quick and easy verification of a user. In a traditional session-based authentication, user issues a login request to a server, and then server validates the user and generates a session ID. Session ID is stored in a database and returned to the user. On a subsequent request, client presents that session ID to the server. Server then validates it against the database and allows for the connection. This traditional approach is great, but it presents some challenges in, for example, distributed systems architecture, where that centralized database, it is really an issue. Therefore, token-based validation comes into play. User issues a login request, and server validates the user. In response to that, it returns a signed token that's been generated by the server. User stores that token, and on a subsequent request, presents the token to the server. Server then is able to computationally validate that token and determine whether a user is allowed for a connection. This is a great approach because token is self-containing, meaning it contains all the information necessary for the verification. It also is stateless and pretty quick compared to the session-based auth, because think database lookup versus a computation operation. One place where token-based auth comes in handy is a WebSocket protocol. WebSocket protocol was created for a quick message exchange, but it inherently does not contain any authentication mechanisms. So we can use token-based auth in a couple of creative ways to accomplish that task. First idea is to include a token as a query parameter in the URL. That is a very straightforward approach, but it's not as secure as one might think. That token can be exposed in the browser logs, or it can be unintentionally exposed during network capture. So this approach has been discouraged. Second option is to get creative with the only customizable header on the WebSocket protocol, sec WebSocket protocol header. In a specification, all it states is that the value of that header has to be a string or an array of strings. So we can take that token, which is a string, and include it as a value of the header, which could work, but as it usually goes with if we use things not the way they're intended for, some implementations of the WebSocket server, they fail to process large tokens, and as you might find later on, tokens can really be huge, and in that case, our auth will fail. So further than fourth option kind of solve that problem. Fourth option is to create a custom payload protocol for each and every single message that we send through our WebSocket, and include a token in that message. Token would be validated on each and every request, but we will make sure that our message is secured. And the last idea would be to send the token as a first message post the connection, and then treat all the other messages as secure until the connection drops. Now onto JWT anatomy itself. JWT contains 3 parts, all separated by the dots: header, payload, and signature. Each part is by itself base 64 encoded. First part, header, contains some information about the token itself. Like, for example, an algorithm that was used to generate a signature. It also can contain a well-known endpoint that can be queried to retrieve a public key that can be used to verify the signature. It can contain a set of public keys by itself, and it can contain a pointer to an appropriate public key that was used in a form of key ID claim. Second part of the token payload is a hard and soul of the token, as it contains a set of claims that can be used to that will be used to verify the user. There are three different types of claims: registered, public, and private. Public and private claims are what allow for some flexibility on the protocol and the specification, where a developer can really get creative and include whatever they wish in the JWT. With that, you gotta keep in mind that this is only applicable for your own scenario, and also if you are just utilizing JWTs, then make sure to check against the specification, like what those claims contain or how they are structured. And there are also registered claims, which are a part of official claim registry, and they have to adhere to the specification included there. A third part of the token, a signature, is what makes a JWT secure. That signature ensures that the token has not been tampered with during transit. It's a bit complicated topic, and in fact, the specification allows for there not to be a signature at all, which obviously that a little bit defeats the purpose of the secure communication if you cannot confirm that it hasn't been changed. But a signature, first to create it, we would first take a header and a payload, so all of the information we want to convey, and create a hash of that. Then we would use that hash and a private key or a shared secret to encrypt that message. And all of that at the end needs to be base64 encoded. Both hashing and encryption allows us to ensure that we can later on compare contents of the token and to contents that were initially generated. So now onto the token validation. There are very well-established libraries that allow you to validate the token, but at times when you introduce any customization in your token, you might need to find yourself in a situation where you need to either validate the token all by yourself or validate parts of it. So first, after we receive the token, and it's this like big blob, we take it and split by the dot to obtain a header, payload, and signature. Then each one of those parts needs to be by itself, base64 decoded, to get to the underlying message. We can start by analyzing a header and comparing the algorithm that was used in a header to the one that we know or expect to be used. If those two don't match, we can straight away just return that the token is invalid. Otherwise, we can proceed and start with the signature verification. So we want to make sure that the token can be trusted and the claims included in the token can be trusted. Signature will be verified by computing our own signature and comparing it to what was sent to us with the token. So we would take the algorithmic function that we retrieve from the header that we expect and take that header and a payload, create a hash of that. Then we would take that and try to compare it to the decrypted signature that was sent with the message. If they match, we are happy and we can proceed. If they don't match, we would have a hint that something is off with the token and token needs to be invalidated. The tricky part is obtaining a public key, where that can be done either through a common well-known endpoint or can be set with the header. Really depends on your implementation. And finally, we can proceed and start claim verification. So usually we would make sure to verify registered claims like an issuer, subject, audience, obviously expiration date, that it hasn't passed. And that's also the place where we would verify any custom claims that we've included in a token. And after all that's beautiful and done and everything matches what we expect, we've confirmed all the formats, we can determine that the token is valid and allow for the connection.